Good evening, everyone. My name is Rajdeep, and today is an extra class for optimization in chemical engineering. It is a course which is offered by Professor Devashish Sarkar from the Department of Chemical Engineering, IIT Kharagpur. So, up until now, we have studied about different optimization techniques which involved only single objective, that is, only one objective. Now, today, we are going to look into multi-objective optimization. Multi-objective optimization are very important optimization techniques which is essential in engineering problems, because usually in engineering problems there is not only one single objective to handle. Usually we have more than one objectives, and whenever an optimization problem there is more than one objective, we call it a multi-objective optimization. It can be two objectives or three objectives or more than that. A common example of a multi-objective optimization may be from a chemical engineering perspective. Maybe a problem, let's say, if we look at the example of a multi-objective optimization, let's say minimization of this is one example. The other example can be minimization of cost and CO2 emission. It can also involve maximization of efficiency and minimization of cost and energy conversion. So these are the few examples of different multi-objective optimization. So if we look into multi-objective optimization, we can see that, as I had said, that most real-world problems involve simultaneous optimization of several objective functions. Now, these objective functions are measured in different units and are often competing and conflicting. And how are they competing and conflicting? Let's say if we take the example of maximization of efficiency and minimization of cost. Now in these cases we know that if we increase the cost, the efficiency of a process will gradually increase. But here we can see that we are trying to achieve higher efficiency at a lower cost, which is competing and conflicting. So this is what the second point means, that usually these objective functions, they are measured in different units. Like efficiency, they have they are unitless, and cost, they are usually depicted as unit of currency per year, which is the total annual cost of a process, and they are competing and conflicting. Like I've said, like for a lower cost, it is very difficult to achieve higher efficiency. Now, since these objectives have such conflicting functions, they give rise to a set of optimal points. Usually what happened previously, we had only one single objective function, and over there we used to get a one global optimum solution. Now when we have more than one objective function, we are going to get a set of optimal solutions. That is not only one unique solution, that a set of optimal solutions, and instead of one optimal solution, because no solution can be considered to be better than any other with respect to all objectives. Now these optimal solutions, they are known as Pareto optimal solutions. Since all of these optimal solutions are equally good to each other. So this is a representation of a multi-objective function, and here you can see that we can minimize or maximize fi of x, where I can be 1 to n number of objectives which are subjected to these equality and inequality constraints. Here fx is the objective function, x is the decision vector that represents a solution, n obj is the number of objectives, k and l are the number of equality and inequality constraints respectively. Optimization problems with a number of objective functions to be satisfied, and the objective functions may be conflicting with one another, as I had said earlier. In order to simplify the solution process, additional objective functions are usually handled as constraints. Now this third point, it is one of the methods of handling multi-objective optimization, but however this is not an efficient method of optimizing a multi-objective problem, because if we handle an objective function in the form of constraints, we might get a solution which will satisfy it, but that won't solve the purpose of our optimization. Multi-objective functions are handled at the same time. This is a much more desired method of handling multi-objective functions. So now we are going to look into Pareto optimality. With a set of feasible solutions and different objective functions to pursue, Pareto improvement is a movement from one feasible solution to the another that can make at least one objective function to return a better value, with no other objective function becoming worse off. So what is a Pareto improvement? Let's say we have m number of Pareto optimal points. If we have n number of optimal points, then in a Pareto optimal set, then all these points are equally competitive. And by the word competitive, it means that at least all of these points may return an objective function with a better value, with no other objective function becoming worse off. Pareto efficient or Pareto optimum is a set of feasible solutions. A set of feasible solutions are Pareto efficient or Pareto optimal when no further Pareto improvements can be made. So if we achieve a point where no further improvement in the objective function can be made by not worsening of any other objective function, then we can say that we have achieved a Pareto optimal or a Pareto or a Pareto optimal set. So what is Pareto optimality? Here we can, in the figure, we can see that these are examples of a Pareto optimal front. Now all these points over here are Pareto optimal points. Now if we take a point, let's say over here, we can take a point A, and let's say if this is point B, and we have two functions f1 and f2, then from this point A, and we compare the values A and B, we can obviously say that B is a better point than A. Now all these points are non-dominated points, that is any point which is within this feasible solution space. This is a feasible solution space. And all the points that form the optimal front of this feasible solution space are non-dominated points. That is, all the points apart from these points are not as good as the points that are present in this front. So here any point that is within this front is a optimal point, and it will satisfy our desired objectives. Now it is not necessary for every front to be of the same shape. Here we can see in this second figure over here that a different geometry of Pareto optimal front is obtained. Solutions along the line are non-dominated solutions. Dominated solutions are inside the line, as there is another solution on the line with at least one objective that is better. The line is the Pareto optimal front, and the solutions on it are called Pareto optimal. All Pareto optimal solutions are non-dominated. It is important to find solutions as close as possible to the Pareto front and as far along as it is possible. Now this is an example of a Pareto optimal solution. There are 9 types of air tickets with different time and cost details. We need to choose from them with objective functions of minimum cost and minimum time. If we compare air tickets, if we compare air tickets A and B, we see that A is better from time point of view and B is better from the cost angle. A and B thus form a non-dominated set. However, if we compare B and C, we see that B is equal to C in time, but it is better than C in cost. Hence, we can say that B dominates C. So, as long as B is a feasible solution, there is no reason to choose C. So, if we consider these 3 solutions over here, A, B and C, so here it is being said that the time and the cost is given. If we compare A and B, we can see that A has a less time than that of B. This is 2 and this is 3. And whereas for cost, A has a more cost than that of B. So A dominates B from the time point of view, since we are trying to minimize time and cost simultaneously. Again, if we compare B and C, we can see that both B and C, they have the same time, but the cost of B is less than cost of C. So if we have to choose between A and B, we are going to, there will be a decision involved, as in the time consumed is less compared to B, whereas the cost is more. But if we have to choose between B and C, we can easily choose B because the cost is less than that of C, B, while the time is same for both the cases. So here we can say that if 9 air tickets to choose from them with objective functions of minimum cost and minimum time, A will dominate C because A has a lower time than that of C and equal cost. Now B dominates C, E, G, H and I. D dominates E, G, H, I and F dominates G, H and I. Thus, A, B, D and F form a non-dominated set. That is, these points are not dominated by any other points, and hence A, B, D and F will form a Pareto optimal front on non-dominated front, and they are the Pareto optimal solution. So here they form a Pareto optimal solution, and now coming to evolutionary optimization. Evolutionary algorithms are particularly suitable to solve multi-objective optimization problems as they deal with a set of possible solutions simultaneously. Evolutionary algorithms are capable to find several members of the Pareto optimal set in a single run of the algorithm. Evolutionary algorithms are less susceptible to the shape or continuity of the Pareto front, and they can deal with continuous or concave Pareto fronts. They are both non-Pareto and Pareto techniques available for multi-objective optimization using evolutionary optimization techniques. So Pareto and non-Pareto evolutionary techniques. Non-Pareto techniques approaches that do not incorporate directly the concept of Pareto optimum. They are incapable of producing certain portions of the Pareto front. They are efficient and easy to implement but appropriate to handle only a few objectives. For Pareto techniques, which is suggested originally by Goldberg to solve multi-objective optimization problems, use non-dominated ranking and selection to move the population towards a Pareto front. They require a ranking procedure and a technique to maintain diversity in the population. So there are different Pareto and non-Pareto evolutionary techniques. We are going to focus on the Pareto techniques, and we are going to discuss about non-dominated sorting genetic algorithm 2, NSGA 2, and we are going to look at examples from multi-objective genetic algorithm. So these two will be, we are going to focus on these two algorithms. We are going to look at the example using MATLAB Toolbox. And this we are going to discuss. So non-sorting genetic algorithm 2, it is an algorithm which was proposed by Kollonmai Dev, or it is also written as Dev et al. In the year 2000, and its key features is that they emphasize non-dominated sorting, they use diversity preserving mechanism, they do crowding comparison, and they use elitist principle, where some of the parents go directly to the next generation based on the above mentioned conditions. So before going into the details of the non-dominated sorting, let me just tell you how this non-dominated sorting actually works. So let's say we have an objective function, we have an optimization problem. Now, depending on this optimization problem, we know the upper bound and lower bound of the different of the variables that we have. Now, there might be more than there might be more than one variable. So, if we know the upper bound and lower bound, what happens is we a set of random a set of random variables are generated. The fitness function, now this becomes the parent population. Few variables are chosen to form offsprings. Now this is an example of elitism. Then the process is repeated until the generation number supplied by the user is achieved. So let's say that first we have a parent population. Let's say we have two parents population from here, and the parent population has, let's say, 5 fitness function values were first generated, out of which 2 were not good. So these 3 populations, so these 3 variables then goes to the first generation. This is, let's say, G1. So this is generation 1. For generation 2, these 3 parents are going to come along with their offsprings. Let's say they are for 3 they are producing 2 offsprings each, so there are more. So what happens, this becomes generation 2. Now all these fitness function values are then evaluated, and again it is seen, let's say, probably for these last 3 values the fitness function is not good. So again these values go into generation 3 and so on. So here you can see that how non-dominated fronts are formed. So non-dominated front 1, non-dominated front 3, and non-dominated front 2, and non-dominated front 3. Non-dominated front 1 is supposed to give us the best optimal solution, Pareto optimal on non-dominated fronts. Now A, B, D and F form a non-dominated set and are Pareto optimal solutions. Next, we are going to look at the non-dominated rank comparison. Given 2 solutions I and J, solution I is preferred to solution J if the rank of J is more than rank of I. Fitness assignment: solutions in non-dominated front 1 are ranked 1 and have the highest fitness. Now solutions in the same front have the same rank and the same fitness. A solution with a solution with lower non-dominated rank is preferred over others. When 2 solutions have the same non-domination rank, that is, they belong to the same front, the one located in a less crowded region of the front is preferred. So first, all the solutions that we are going to get in case of a multi-objective optimization, there will be a set of Pareto optimal points. Now there will be a set of optimal solutions. Now in order to achieve the set of solutions that are Pareto optimal, we are dividing it into different non-dominated fronts. Now after they are differentiated into fronts, what we are doing is we are ranking them. So given two solutions I and J, a solution I is preferred to solution J if rank of J is more than rank of I. The solutions in the non-dominated front are ranked 1 and have the highest fitness. And all the solutions that are present in the non-dominated front 1 have the same rank and the same fitness. A solution with a lower non-dominated rank is preferred over others. So when two solutions they have the same non-domination rank, so how do we select a point which is which have the same non-dominated rank? We go for the evaluation of the crowded region, and we select that point which has a located in a less crowded region than the others. So convergence to a Pareto optimal frontier is that the algorithm, it always pushes the convergence towards the non-dominated front, and the diversity it is the representation of the entire Pareto optimal frontier. More the crowding distance, more is the solution is likely to be retained for diversity preservation, and the diversity is can be measured or can be seen by the extent of the non-dominated front, as to how much the non-dominated front is spread over the solution space. So here this is a key feature of the diversity preservation of the crowding distance. There is an example of a graph which is given over here with two functions f1 and f2. So how do we calculate the crowding distance is that we sort all the solution in the Pareto front in an ascending order of fm, and we compute the crowding distance as fm x I plus 1 minus fm x I minus 1 divided by fm into x max minus fm into x min, and we repeat this step for each objective and find the crowding distance of the solution. Now given two solutions I and J, solution I is preferred to solution J if the rank of J is more than rank of I. Now if both the ranks are same, then we go for the crowding distance. That is, more the crowding distance, more the solution is likely to be retained for diversity preservation. For the example that we had seen earlier, if we have to calculate the crowding distance, we can see that crowding distance for point A and point F, since they have no neighboring points around them on either side, so we can say that the crowding distance for both these points are infinity. Now coming to point B, if we look into this table over here, the function of time, the largest value is 6 and the minimum value is 2. Again from the cost objective function, we can see that the largest value is 7.5 and the minimum value is 4.5. So if we have to calculate the crowded distance for point B from the formula, So depending upon the crowding distance function that we had seen, we can see that crowding distance can be calculated as 4 minus 2. That is, if we are calculating for the point B over here, so the neighboring points are D and A. So 4 minus 2 divided by 6 minus 2, that is F max minus F min. Then plus we have the second objective function where we have 7.5 minus 5.5 divided by 7.5 minus 4.5. So the crowding distance comes at 1.33. Similarly, we calculate the crowding distance for point D and we get the value as 1. So from these four values, if we have to choose which one we have to choose, that is the ones that have the highest crowding distance values. So CDA and CDF will be chosen because that is A and F, since the crowding distance values are infinite in these two cases, and out of B and D, B will be chosen because it has a higher crowding distance value compared to D. Now we are going to look at a sample problem from and we are going to see how to solve multi-objective optimization problem using toolbox, that is GA multi-objective toolbox in MATLAB. That is, we are going to see the GA multi-objective toolbox in MATLAB, and this is the problem that we are going to solve. That is, a rectangular open top box is to be constructed subjected to some given conditions or constraints. So what should be the dimensions of the box so that the surface area of the box is minimized and the volume is maximized? Now this is a multi-objective optimization problem that has both maximization and minimization, and we can see that we have three variables over here, that is the height of the box, the width of the box, and the D, that is the depth of the box. Now the inequality constraints are given over here with upper bounds and lower bounds, and if we try to imagine this problem in a physical sense, as in we have to maximize the volume and minimize the surface area. So surface area minimization means that a lower cost has to be incurred, because higher the surface area, more will be the cost of production of the box. That is, at a lower cost of production, we want to have more space to hold things. That is, we want to maximize the volume at a lower surface area. So we are going to see how to solve this using MATLAB. So first what we are going to do is we are going to create a script file. Let's say so first we are going to create a script file for the objective function. So let me write it, give the name of the script file as now we have three variables, that is depth, we have the height of the box. X is actually an input vector where we can insert n number of variables inside X. So the function f1 will be the surface area, so this is the volume of the box. So after this is done, we need to save this. Next, we have to make another function file which involves all the constraints. So there are two constraints, which is inequality constraint, and usually inequality constraint is only present, but for the generalization purpose we are going to write it the equality constraint also. I'm going to name it as So we have to write the inequality constraints in less than equal to form, which is the standard form in MATLAB. Since we don't have any equality function, we are going to give an empty matrix over here. Now we did a mistake over here, like since we have to increase the volume of the box, and MATLAB in general always treats every objective function, every optimization problem as a minimization problem. So in order to maximize a function, we need to add a negative sign over here in order to optimize, in order to maximize a particular problem. So let us save this file also. We save as. Next we have to form the main file. So before that, let us look into the multi-objective, how the function is written. First we are going to save this file into the directory where we have saved all the function files. So in this directory we are going to save this file and let this be the main file. So first we are going to call the function. When I have written this as @mo objective function, this file is going to be called. Next we are going to set the number of variables. Since we have already written the constraints in a separate function file, we are going to keep this matrix empty. Next we have the lower bound. Then we have the upper bound. Now we are going to call our constraint file. That is this file over here. So now we are going to write what all we need. That is, first we are going to need x, that is the decision variables that we are going to get. Then we are going to take the f value, that is the function value. Then we are going to get the exit flag and output. First is the function, then the number of variables. This is for the inequality constraint. Since we have already written it in a different function file, we have kept it as empty matrix. So it seems that I did not have this add-on, so let me install it and then so this is how we write the objective function, or how we use this GA multi-objective function to solve multi-objective optimization problems. So we have already written this, and now we are going to run and see the solution from it. So here it says exit flag 1, which means the optimization has been done properly, and the problem time is a nonlinear constrained optimization. Next we have the generations 104, and this is the total function count that we have got, and these are the function values that we have got over here. Now the value over here is negative. It is because we wanted to maximize this function. This is the volume and this is for the surface area. Next, these are the objective functions that we have got, or these are the decision variables, that is the depth, width and height of the rectangular box. So next is how do we, and the most interesting thing about this genetic algorithm multi-objective functions, every time we run this program we are going to get different objective function values over here. Like if you see this value over here, if I run this function again, we are going to get different function values because the decision variables that are chosen over here, they get changed. So I'm going to show you one example. Now you can see that again this objective function values, they have changed from the previous set values. So we are segregating the surface area into this variable as, and we are forming a table using these two variables. Next, we are going to sort this table. Now we are going to sort it with As. Since we have to convert this, the volume value was in negative, so we have to convert it into positive. So we are multiplying a minus sign over here. Now we are sorting it based on surface area. Next, we are going to extract these sorted values. Now we are going to plot these values. Now let us run the file again. So here we can see that a Pareto optimal front has been obtained like this. So this is how we use it without using any toolbox. Now let me show you how to use it using a toolbox. So we are going to select app. From here we are going to select optimization. Next we are going to select the solver. So we are going to solve it using this problem. So we have to give our fitness function, that is the function files, and in here we are going to write it as this function file over here, mo objective function. Number of variables is 3. We are going to keep all this empty because we have already defined all the constraints in this function file. Next we are going to keep all this unchanged. What we are going to do, we are going to plot the Pareto front, and the level of display will be iterative. That is, for every iteration we want to see the values, and then we are going to give start. So here you can see how the Pareto fronts are being formed for every iteration, and this is going to be formed as long as the entire problem converges. So now you can see that the problem has converged. Here it has said that the optimization is terminated, and this is the value. This is F1 is the volume. Since we are maximizing it, we are getting it as negative, and F2 is the surface area. Sorry, we forgot to give the lower bound and upper bound over here. That is why there has been an error. So let me give the lower bound and upper bound. So here is the value over here. Over here also they are giving the values. This is the final Pareto front that we have obtained. Since this is in negative, the Pareto front which we had obtained earlier, it is just the opposite of that. We can extract the values and change it manually also, but for that we need to extract the values, and for extracting values from this function file, we can go to the function file, export to workspace, export results from MATLAB structure name optim results, and if we click OK, so in the workspace we are going to get this structure file. with these values. So here is the x value, that is, this is the decision variables over here, and this is the function values. So this is how the optimization toolbox is used. So Diaz, can you unmute yourself? Hello, am I audible? So I hope my screen is visible now. So the question that was given is we want to build a box whose base length is 6 times the base width, and the box will enclose 20-inch cube. The cost of the material of the sides is $3 per inch square, and the cost of the top and the bottom is $15 per inch square. The minimum cost of the box in dollars up to 2 figures after decimal using function fmincon is: take initial guess as length, width, height 1, 1/6 and 120. So this is a drug manufacturer makes three types of products A, B, C. 5 formulators are needed for this purpose, and the time required for each product on the machine is given below. Each formulator is available for a maximum of 6 hours per day. If the profit on each product of type A is rupees 7.50 and 5.50 and for C is 6, the maximum profit that can be achieved in a day. You have to use LeanProg. So let X be This is the entire objective function which we have to solve. So this is coming in negative because we had to maximize this problem, and this is the answer. So with this we come to the end of this class. Thank you.